So in this lecture series, we shall learn how we can do the non-linear pushover analysis of a structure. So all the analysis method that we use for the design and evaluation of the performance of the structure are basically classified into four types. Number one is the linear static. Number two is the linear model response spectrum analysis, that is linear dynamic analysis. Number third is a non-linear static analysis, that is pushover analysis, that we shall cover in this lecture series. Number fourth is a non-linear dynamic analysis, that is time history analysis. So how exactly was this non-linear pushover analysis term derived, or why do engineers think of this term? So basically what happens is that the structures are designed for the forces which are much less than the expected design earthquake forces. So when a structure is struck with a severe earthquake ground motion, that is the actual force that shall come on the structure, it undergoes an elastic deformation. So you must be thinking why we are saying that the structures are designed for much less earthquake force as compared to the original earthquake force that shall come on that structure. Because if you remember the basic formulas of the calculating base shear in a structure, in formula what we do is that we divide the actual base shear value with the response reduction factor. So that response reduction factor is a factor by which we decrease the earthquake force. So if we are using response reduction factor as, let us say, 5, so we are designing the structure only for 1/5 of the actual earthquake force. So what will happen if we are designing the structure for the lesser earthquake force? So if we are going for the ductile detailing, so in that case structure may not collapse, but the damages can be beyond repairs. So that is why structures are made ductile, and a sufficient ductile structural system may undergo large deformation in the inelastic region also. So that is a basic fundamental, that each and every material has a elastic range, that is the range in which the strain that material or strain of that material may come on to again to 0. But in the case of the a sufficient ductile structural system may undergo large deformation in the inelastic region also. So in order to understand the complete behavioral structure, time history analysis of single degree of freedom STOF or multiple degree of freedom, that is MTOF, having non-linear characteristics is required to be performed. And the results of this non-linear analysis will help us in understanding the true behavior. And once we are done with this either non-linear static analysis or non-linear dynamic analysis, we can ascertain or we can classify that the structure will collapse or structure will not collapse, or structure may be 100%, let us say, elastic. So when we classify the non-linearity, it is basically classified into two types. Number one is stiffness and number two is a damping non-linearity. Under the stiffness non-linearity, again there are two types, that is geometric non-linearity and material non-linearity. Damping is somewhat somewhat higher or too complex to calculate or too complex to check in a structure. So that is usually encountered in offshore structures or aerodynamics of structure. But most of the times in our day-to-day structural dynamics, we use geometric nonlinearity and material nonlinearity. So under geometric nonlinearity, hysteresis behavior is not exhibited, but under the case of material nonlinearity, restoring action shows a hysteretic behavior under the cyclic loading. So the next graph will show us that this is the geometric nonlinearity, that is no hysteretic behavior is exhibited, but this is a material nonlinearity. So this graph is showing hysteresis curve. And now the question, that is why we need to do the pushover analysis. So pushover analysis, as we had discussed in the previous slides also, that is earthquake forces are random and unpredictable, and earthquake loads are to be carefully modeled to assess the real behavior of structure. So that is why this pushover analysis has been looked upon as an alternative for the conventional analysis procedures. So pushover analysis can be done for the RCC frame buildings also and for the structural steel buildings also. And in simple words, it is a static nonlinear procedure in which the magnitude of structural loading along the lateral direction of the structure is incrementally increased in accordance with a certain predefined pattern. So in almost all the designing softwares, let us say if we talk about the STAAD or SAP 2000 or e-tabs or Midas Gen or Midas Civil or Proto Structures, almost all the softwares have the option to do the pushover analysis. So there are basically two types of pushover analysis. Number one is the force controlled and number two is the displacement controlled. In force control, this is the behavior of the structure we check, and under the displacement control, this is the behavior of the structure we check. So under the force control, the total lateral force is applied to the structure in small increments, and this type of force control pushover analysis is not preferred. But under the displacement control analysis, the displacement of the top story of the structure, let us say this point, is incremented step by step such that the required horizontal forces pushes the structure laterally. And displacement control pushover analysis generally preferred over the force control because the analysis can be carried out up to the desired level of displacement here. And this is the capacity curve that has been extracted from the STAAD.Pro software after doing the pushover analysis. So this type of example we shall check in our next lecture, but this is just a preview of how this analysis is showing us this green and blue color, that is the color of the hinges that has been formed in the structure. So non-linear behavior do occur in discrete user defined hinges, and the definition of hinges can be checked from the FEMA, that is FEMA, or it can either be derived from the ASCE manuals also. So hinges can be introduced in both the frames as well as the vertical wall objects, and hinges may be assigned to any location along the frame object but are restricted to mid height in the wall object. So STAAD does not offer us to model the hinges in the walls. e-tabs and Midas do offer us this option, and the basics of why we do the pushover analysis lies in the response rotation factor R. This I had already explained in the previous lectures also. So you should know that we never analyze for the full earthquake. You already know that I had already explained in the previous lecture, but we also does not analyze for the ductile part. So that we follows the latest reinforcement detailing guidelines for the same, and it is like an assumption that if we do the reinforcement detailing guidelines correctly as per the latest earthquake design standards, the structure shall be ductile in the post elastic zone, that is plastic zone also. Hinges may form but the structure may not collapse. So elastic analysis do gives us a good indication of elastic capacity of the structures, but it cannot account for the redistribution of forces during the progressive yielding that follows and predicted failures mechanism. So again, this is the definition of the pushover analysis. So what are hinges? Some of you must be thinking that I had already used this word in the previous slides also. So hinges are points on a structure where one expects cracking and yielding to occur in relatively high intensity. This line, you should read it again. That is, the hinges are the points on a structure or structural elements, we can say, let us say beams or columns or beam column junctions, where one expect cracking and yielding to occur in relatively higher intensity, so that they show high flexural shear displacement as it approaches the ultimate strength under the cyclic loading. So these are the locations where one expect to see the cross diagonal cracks in an actual building structure after the seismic forces, and they are found at either ends of the beams or columns. And hinges can be of various types also. This is also a very important point, that is the design guidelines to classify the hinges into various options, that is flexural hinges or shear hinges or axial hinges. e-tabs do offer us to model this flexural, shear or axial hinges separately, but STAAD does not offer this option. So this is basically a simple diagram here. Here you can see that In this bracing section here, the hinges that has been formed shall be of axial type. And in the column you can see that the beam, you can see that the hinges that has been formed are of either flexural or shear hinges. So this is the general graph here. So this is the bending moment and this is the theta, that is the radius of the hinge that has been formed. So as per the various design guidelines, theta is a deciding factor that whether the hinge shall be of immediate occupancy or life safety or collapse prevention. So if you are into somewhat basic structural analysis, you must have heard this term, that is the hinges are of three types, that is immediate occupancies, life safety and collapse prevention. So the code has given us a guideline that is for some theta value, let us say this is theta value, the hinge shall be of immediate occupancy. For this theta value it should be of life safety, and for this theta value it shall be collapse prevention. So all the hinge properties can be obtained from the charts of average value indicated in FEMA 356 or ATC 40 or FEMA 440 for the accurate results. One would require details of reinforcement provided in order to calculate the exact hinge properties. So in ETABS, or in, let us say, in SAP 2000 or in MIDAS, if you are doing the pushover analysis, the software will ask us option that what is the reinforcement that you are putting in the beam. So it is like we do not say that only concrete will like stand against the earthquake. We think like that is the rotation and all the hinges that shall be formed, reinforcement shall be equally responsible also. So all the good softwares do ask us about the what exactly is the reinforcement in the beams and columns while doing the pushover analysis, and what exactly are the reinforcement in the ductile zones also. So that is also asked in the ETABS and SAP software or in proto structures, let us say. But in STAAD, they only offer us an option to do the pushover analysis for the steel structures only. They don't offer us an option for the RCC structures. So pushover analysis is meant to be a second stage analysis. This is a very important line that you should understand. That is, pushover analysis is a second stage analysis. That is, first of all, you shall design the structure, you shall calculate the reinforcement, you shall again put that reinforcement into the software and again do the pushover analysis. So that is why it is called the second stage analysis. That is, in first stage you do the basic analysis and design as per your earthquake design standards, and then after that you again put the reinforcement in the software and then check that what exactly is the performance of the structure, that is whether the hinges forms are in IO range, that is immediate occupancy range, LS range, that is life safety range, or CP range, that is collapse prevention range. So the methodology to an accurate seismic design is first a linear seismic analysis is performed, after that the hinges are modeled, then pushover analysis is done, and then accordingly, if required, we shall do the modification in design and detailing wherever is necessary as per the pushover analysis results. So these are some of the advantages. Obviously, if you are following this lecture correctly, you can say that what exactly are the advantages. That is, you can do the performance assessment of the structure, and it can also help us in fine-tune the seismic design based on the static analysis. So what exactly is the difference between static analysis and pushover analysis? So static analysis is a linear analysis, that is all the elasticity is only considered, but in pushover analysis there is a non-linear, and gravity and lateral loads are also applied sequentially in a single analysis, and plastic level of forces are also considered in the design. So pushover analysis is used to stimulate the behavior under the actual loads, and loads applied are not factored. So thus in pushover analysis, the gravity loads are applied in accordance with clause 7.3.3 and table 8 of IS 1893. That is, and static analysis, lateral load of calculated density is applied in whole in one shot. So in pushover analysis, structural model is gently pushed over to momentarily increasing lateral load applied in steps up to predetermined value of state. Here this load can be displacement in the displacement type pushover analysis. So hinges are inserted in the structural members of a frame structure. Then the hinges have non-linear states defined as IO range, LS range, or CP range. And there are various assumptions also, that is material needs to be homogeneous and isotropic, all columns are considered a fixed at the foundation, tensile strength of concrete is ignored, and pushover analysis are assigned to all the member ends. So in case of, let us say if we are doing the pushover analysis in the E-tabs, so PMM hinges are classified, that is PM to M3 are axial and moment hinges, while in the case of beams only M3 hinges, that is bending moment along the major axis is provided. And if we are modeling the bracings also, then we shall provide the axial hinges. But all these options are not available in the STAAD software, they are only available in the E-tabs and SAP 2000 software. And maximum target displacement of the structure can be calculated. American standards, that is ASCE 0716, gives us the guidelines to calculate the maximum target displacement of the structure in accordance with the various parameters, that is height or or various other dependent parameters of the structure. So classification of performance, this is also a very common interview question also. That is how we can assess the classification of performance of the building. They are basically classified into 5 levels. That is operational, OP, immediate occupancy, IO, LS life safety, CP collapse prevention, and damage control, that is DC range. So I hope things are now clear to you. That is in this lecture series we have learned a lot of things. That is what do you mean by pushover analysis. If you are new to all this analysis, you shall also be surprised that we also go in the plastic range also. It is not like we restrict ourselves to the elastic range, but as I had again repeated in the various slides, that STAAD is offers us a very limited options to do the pushover analysis. It only offers us to do the pushover analysis of the steel framed structures. It does not offer us an option to do the pushover analysis for RCC frame structures. So you study various types of non-linearity and what are hysteresis curve, what exactly do we mean by pushover analysis, what are the advantages of doing pushover analysis, what are the types of pushover analysis, and what is the capacity curve. So in the previous lecture we have learned about what are the basics of the pushover analysis. Now in this lecture we shall again learn the basics of pushover analysis specifically for the STAAD.Pro software. So if you open the help manual and when you search for the pushover term here, so it is explaining that the purpose of pushover analysis is that it is basically the set of procedures to implement a pushover analysis as defined in the document FEMA 356 that was released in the year 2000. And as discussed, it is a static non-linear procedure in accordance with FEMA 356 specifications. So under this method, what we do is that we laterally push the load and increase it progressively according to a predefined loading pattern until either loading or the deflection reaches the described level. So basically, first of all, you need to model the structure on which you need to do the pushover analysis, and then after that we need to go to the definitions here. So under the definition there is an option called pushover definition that we will study in the next lecture, but it is explaining how you can do the pushover analysis. So after that we need to define the inputs, and then we need to define the load patterns, spectrum details, hinge properties, and then solution control. So we shall also try to model this type of structure in our in the STAAD.Pro software, and then we shall try to do the pushover analysis. So here we can see that first of all it shall ask about the inputs. So under inputs there are various options, that is we need to define the type of frame, and then after that we need to define the type of geometric nonlinearity effect, and after that convergence criteria, and after that we have we need to see the output results, and after that under the load patterns it shall ask that if the loading is set to auto or it is set to the vertical distribution of base shear or method of lateral load calculations. After it shall also ask about the spectrums here, and under the spectrum it shall ask about the damping and side category, and after that it shall define the hinge properties. So under the ETABS you shall refer for you can refer for various type of hinge properties. Either you can refer for FEMA or ATC or ASE, but under the STAAD it shall only offer us the option to model the hinges as per the FEMA specifications or user defined specifications. And then after that, how we can do the solution controlling. That is, either we need to define the push up to the defined base shear or up to the defined displacement levels. And then after that, we need to add the perform pushover analysis. Like we under the normal analysis, we do add perform analysis, or under the p delta we do need to add p delta analysis. But under this type of analysis, we need to add perform pushover analysis. And then after that, under the results mode, there is this separate mode called pushover mode. So under the pushover mode, you can see that there is a capacity curve here, and under this capacity curve here, you can again we shall again see that in the next lecture, that how we can refer to the modification factors C1, C2 and C3, and how we can calculate the or how we can show the data points in your curve. And then after that, we can also see the beam results, that is in which beam at what level or at what deflection the hinges are forming. So under the coloring criteria, basically greens means the immediate occupancy, blue means the intermediate between immediate occupancy and life safety, magenta color means that the life safety and collapse prevention, and red means the collapse prevention hinges. So there are also various restrictions, that is perform pushover analysis can be only used once, and load combination command is not accepted. That is only for pushover analysis shall be only done for the loading or not for the load combinations. And Y should always be up, and Z global axis cannot be up when we are doing the pushover analysis. And as discussed, only steel structures can be considered. Non-prismatic sections cannot be used for pushover analysis. Cable specifications on members cannot be considered. On plate and solid elements, we cannot do the pushover analysis. So these are various restrictions that has left us with us not much options or not much flexibility to do various types of pushover analysis. Like we cannot model the hinges in the RCC walls, or we cannot model the specific like axial or moment or various type of hinges. So it is just like somewhat an old concept that I must say that STAAD is still following, whereas other softwares are very much advanced in all these types of analysis. But in this lecture, I just wanted to teach you some basic concepts of how you can do the pushover analysis in your day-to-day office. In the previous lectures, we have learned much about the theoretical aspects of the pushover analysis. So in this lecture, we shall learn how we can do the practical pushover analysis in the STAAD software. So first of all, we shall go to the editor file here. We shall enter the units as meter and kilonewton, and then after that we shall enter the joint coordinates, and we shall enter the origin as joint number 1. And then after that we shall press Ctrl C Ctrl V option, or we can go to the translation repeat option here, and then X we can enter here as 3 meters and number of steps as 2. And then after that we shall translation repeat along Y direction. Default step spacing we can select it as 3, and we can go for link steps here. And then after that we shall again go to the translation Y option, select global direction as Y, and default step spacing we can select it again as 3, and we can go for link steps option here. Number of steps selected as 3, and then go for link steps option. And then after that we can go for support, and we can create a fixed support here. After that we can go to the load and definition option. So this was the option that in the previous lecture we have learned in the help manual. So here you shall get an option to do the pushover definition. So here first of all we shall enter the type of frame. Type of frame we can enter it as moment frame, and geometric nonlinearity effect, here we can go for ignore effect, and we can left click on add here. After that we can again go for this loading pattern here. Loading pattern we can select it as auto, and number of push load steps we can select it as 250. Spectrum detail we can select it as class A. SS we can select it as 1, and S1 again we can select it as 1. Left click on add here. Hinge property we can enter it as per the FEMA, And solution control, we can go for this push up to the specific horizontal displacement, and node we can select as this number of joint, that is joint number 14, and in displacement value we can select it as 150 mm, and then left click on add here. And we can go for save output results. Displacement increment value we can select it as 0.1 meter, and then left click again on add here. So hinges FEMA we can left click on assign to view, and after that we can go for load cases details. Here we need to enter this gravity, and here we can select it as load case number 1. We can select the member load, and here we can enter minus 0.5 kilonewton per meter. After that we can go for this property option here. We can go to section database, under section database option we can select here as American, and we can go for W24 into 55. So W24 into 55 means that the height of this channel or W shape or I shape section is basically 24 inches, and these are the thickness of the flanges and web in inches, and 55 is nothing but the weight in per foot. So left click on select here, and then left click again on add. After that we can go for W16 into 26 for beams. So we can go for select beams parallel to x-axis. Here we can enter W16 into 26, and then after that we can go for W24 into 55. So now all the beams have been assigned a property here, and after that we need to go to the analysis, and here we need to select the perform pushover analysis, and then left click on add here, and then after that we can do the analysis. So here we can see that the pushover analysis is being performed here. And we can go to done here. After that we can go to the post processing mode. So here we can see that there is a new option called pushover option. So under the pushover there are again 4 options. That is, we can again check the loads, capacity curve that has been generated like this, node results, and beam results. So first of all we can check the beam results here. So we can go to the left click on the select load step 1, and then you will see that when we go to load number 7, immediately the hinges start becoming here. So we can see the formation of the hinges here as per the various load steps. So now the base shear has been like increased to the 652 kilonewton, and here there are 1, 2, 3, 4 and 5 hinges, and these 5 hinges, as per the help manual of the STAAD, we can open the help manual also. So color pattern for green hinge was that it is the immediate occupancy hinge. So this was the color coding here, and after that we can increase the steps here. So here you can see that now at this particular point, when the base shear got increased to 778 kilonewton, and the hinge between the immediate occupancy and life safety is we can see here. So blue denotes that the hinge is between the immediate occupancy and life safety level here. So now we can see that all these 4 beams have now got into that particular behavior, and at this particular point here the color has become red here. So it means that the hinge has become gone to the collapse prevention here when the base shear got increased to 825 kilonewton. So this was the different behavior when we are increasing the load steps from load number 1. As our first hinge formation is, we can see at 622 kilonewton and at this particular joint here. So similarly we can see the behavior from here also. So at the load case now, as load step 16 and base shear of this particular value here, now the some beams are in immediate occupancy, some beams are in life safety, and some beams are in collapse prevention. Some columns are in collapse prevention stage. So this was the basic assessment of the structure for the pushover analysis. And then after that we can see the node results also. So at node results it will only show the displacement here. After that, when we can see the capacity curve here. So this is a very important curve. So if you are in your masters or PhD, you must be doing various types of permutation and combination or studying about the behavior of the capacity curves. So if you are new to this, all these pushover thing, I shall recommend you that please do study about the non-linear analysis of a structure. It is much more important to learn about the non-linear analysis as compared to the linear analysis of structures, because that is what shall non-linear behavior, if that behavior is good, it shall only prevent the structure from collapse in earthquakes or in the case of severe winds. So here this is the capacity curve. So here we can see that this is the value 826 kilonewton and the displacement control joint is 151 mm. So when we left click here, it can gives us three options here. That is, either we can show the data points here, and after that we can left click on determine target displacement. So when we left click here, it will again open up a new window. So we can select it as other buildings, loading type we can select as any load pattern, number of stories we can select it as 3, and when left click on next here, so damping we can select it as 5, and we can select the frame as steel moment frame, and number of stories 3 or more. So CM we can select it as 0.9 here. So left click on next here. After that, here we can see that structure performance, we can, if we want it for immediate occupancy and framing type, we can select it as type 1, and when left click on finish here we can see the original and idealized curve. So the calculated target displacement is 67.63 and base shear target displacement is 624.678 kilonewton. And when we again left click here, if we go for this collapse prevention, and when we left click on finish here we can see that again this target displacement is 67.63 and base shear target displacement 624.678 kilonewton. So this is the idealized capacity curve. So I hope the things are now clear to you, that how you can calculate the capacity curve and how you can calculate the target displacements and how you can calculate the base shear at target displacement level. Basically, I must say that pushover analysis is not as simple as this software is showing. It is a highly complex, and but the only disadvantage of pushover analysis is that it is not recommended for the complex structures. So wherever there are complex structures, we do need to go for non-linear dynamic analysis, or if the structures are somewhat less complex, we need to go for linear dynamic analysis. In my practical office life, I seldom use this pushover analysis, because I know the people trust over this type of pushover analysis is not that much good. Plus the code also guides us. American ASCE and Euro codes are the only codes that guides about the pushover analysis and the various specific parameters that we need to take. And I must say that the code themselves say that if your structure is complex, you cannot go for this pushover analysis. Like for example, when your structure has dampers, or even when your structures are isolators, base isolators, then the code does not recommend you to go for this pushover analysis. That is a highly approximate method. So if you I must say that you should know how to do the pushover analysis, but whenever you are stuck in a complex problems, I must say that you should always go for non-linear dynamic analysis or time history analysis, because that is the best analysis that our structural dynamics can offer us. So I hope the things are now clear to you, that how you can do the pushover analysis, what are the basic theoretical aspects, and what are the practical guidance to do that in the STAAD software. And as a general exercise, what we can do, we can increase the size of this beam. Let us say we increase it to some higher size, and we can increase this column also to some higher size. And when it is considered as an exercise for you, and when you will increase the size of these particular columns and beams here, you will see that the hinges that were starting getting visible in, let us say, load step number 5 or 6, they may not be visible to you again, because when we increase the stiffness of a structure, obviously the hinges that were getting visible at particular load steps, due to the strength of that member, the hinges may become visible at later steps, or it might happen that when a structure is very, very strong, the hinges may not happen. So do try various 3D structures also, 2D structures also, and if possible model a bracing also, and then check the behavior. And you can increase the size of these columns, and when you will see that if you decrease the size of this column and beam, you will see that the more hinges are formed in the structure. So obviously when your structure is weak, more hinges will be formed, and when your structure is strong, lesser number of hinges will be formed.